Hi folks, we're going to take up the second part of the October 30th lesson here. So here I'm asking you to label this diagram with these terms that relate to defining angles on a Cartesian plane. Okay, so we talked about it earlier that in the past we would have defined trig ratios by working with right angle triangles. Okay, and we'd use the acute angle and then define the trig ratios using that angle inside the right angle triangle. But of course, once we have angles that are greater than 90, we can't fit them into a right angle triangle. And even though we can fit some angles greater than 90 into, say, an obtuse angle, an obtuse triangle, certainly once we get past 180, we're done. So we use this other perspective on defining angles. Okay, so here an angle is defined as starting from the positive x-axis and then turning towards what we call a terminal arm. So terminal arm is just this line that radiates from the origin. So here we have our terminal arm. Okay, and in order to define the trig ratios, what we do is, instead of working with opposite, adjacent, hypotenuse, you would have seen last year that we can, again, if we think of this as being on a Cartesian plane in the first quadrant, we realize that the opposite side to your angle is just the y value to any point on the terminal arm. Okay, and it can be any point because, as you saw in grade 10, the ratios remain the same regardless of how big the triangle is. And here your adjacent side just becomes your x value for that point. Okay, so this is why we can use points on the Cartesian plane to actually help us define angles. So here what's nice about this is it could be any point on the terminal arm. So any point on the terminal arm will work in defining the trig ratios for these angles. Okay. Next we have related acute angle. Well, we know that sometimes it's still useful, especially when working with our special triangles, to work with a right angle triangle. And what we call the related acute angle is that angle between the terminal arm and the x-axis, whether it happens to be, in this case here, the negative x-axis, or if we were somewhere down there to the positive x-axis. This is our related acute angle. Okay. And lastly, it's also useful to split up the Cartesian plane into our four quadrants. And so here we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay, so now let's use all this to define our trigonometric ratios for any angle. Okay. By the way, another thing we should say about these angles is I've drawn the turn going counterclockwise. Okay, so what that does is it defines a positive angle. If we were to move in a clockwise direction, that would define a negative angle. Okay, now you sort of wonder, why in the world would we define negative angles? Might not make sense physically, but remember, eventually we're going to take these trig ratios and we're going to define functions with them. And of course, there's no need to limit ourselves to a domain of only positive real numbers, but we're going to allow for negative real numbers. So that's to come. But for now, let's define our trig ratios. And so again, starting with this idea of, opposite can be now replaced by the y value of a point on the terminal arm, and the adjacent can be replaced by the x value in the terminal arm. This is how we define now trig ratios for angles bigger than 90. Okay, is we define sine of an angle theta as the y value, okay, over, well, let's go back here. Well, remember, we also need the hypotenuse. Okay, now in terms of talking about x, y, and z, we don't call it the hypotenuse, but we call that the r value. Okay, so y over r. But it's very important to remember what the relationship is between the x, y, and r values. Okay, and we realize that, hey, it's just a Pythagorean relationship. Okay, so here on the side, we'll just recall that r is given by the relationship r squared equals x squared plus y squared. Okay, now notice here you're squaring both x and y and then adding them together. So regardless of whether x and or y are negative, this r value is always going to be positive because we're taking the positive square root when we solve for r. Okay, so r is always going to be a positive number. And so let's keep going. Now we've got cosine of theta instead of adjacent over hypotenuse is going to be x over r, and tangent is going to be y over x. And then of course we have our reciprocal trig ratios. So here we have cosecant of theta, well, is just 1 over sine, or in other words, the reciprocal of y over r, so r over y. And then secant is just x over, r over x, and then cotangent is just x over y. Okay? So here we're defining these trig ratios not by sides of a triangle, but by using a point on the terminal arm. All right? Now, especially useful in the past when they didn't have access to calculators quite so easily, but even to solve problems where we get some exact answers is we've got what we call our special triangles. Okay? Now you'll notice when I draw them, I really exaggerate, the smaller angle here, just so that I don't mix them up. So I've got my triangle, which has dimensions 1, 2, root 3. So you see that by drawing this with a very small angle here, I remember, yes, this must be the longer side compared to the height. Okay? Now, of course, you would have known this as your 30-degree triangle, but now we're not going to think about it as a 30-degree triangle anymore. We're going to think of it in radians. So remember the relationships, pi radians for every 180 degrees. So if this is 30 degrees, I need to divide 180 by 6. So this becomes pi over 6. This is now the pi over 6 triangle. Okay? Then we've got the one with the two equal sides. Okay? The 1, 1, root 2 triangle. Of course, we used to call that 45 degrees, but now we think, if I do 180 divided by 4, I get 45. So in other words, this is going to be the angle pi over 4 radians. Okay? And then again, I'm really going to exaggerate the longer side here. So 1, 2, root 3. Okay, so now this is the larger angle. This is 60 degrees, which of course is just 180 divided by 3. So in radians, it's just going to be pi over 3. Okay, so while these, were certainly useful, they're useful for more than just talking about the angles pi over 6, pi over 4, pi over 3. Okay, because you realize that if I now take these angles and I look for an angle, say here I've got my pi over 3 angle. If I take an angle in the second quadrant whose related acute angle is pi over 3. Okay, so what would this be? This angle here, again, the actual angle starts from the positive x-axis. I realize, well, it's just pi, 90 degrees. Okay, and here, pi over 2. All the way down here is going to be pi, 180 degrees. So in order to get this angle here, I do pi minus pi over 3. So pi is just 3 pi over 3 minus 1 pi over 3 is equal to 2 pi over 3. Okay, so this angle here is 2 pi over 3. You might sort of say, well, why is this also a special angle? Well, because if I look at an x and y point on this terminal arm and I compare it to an x and y point on that terminal arm, I see that they create triangles that are the exact same size. Okay, the only difference is instead of having this, they both have positive y values, but the only difference is they have negative x values to each other. Okay, so of course we're going to see, and we'll start with that next class, we're going to see how we can use this relationship in order to determine sine, cosine, and tangent of that particular angle. And of course I can also do the same thing. Take it down to the third quadrant with a related acute angle of pi over 3. Okay, so the whole angle here, I'm getting a little messy here. Well, instead of being pi minus pi over 3, it's pi plus pi over 3, which is going to be 4 pi over 3. Okay, so the last thing I want you to do for today's class is see if you can come up with all the special angles between 0 and 2 pi. So using pi over 6, pi over 4, pi over 3. And the other thing I want you to think about is, are there other special angles on the Cartesian plane that don't involve your special triangles? And what I mean special is I mean easy. So if you think about it, there's 4 more nice angles on the Cartesian plane for which you can find sine, cosine, and tangent easily. Okay, that's it for now.